Good day, viewers. So today we are going to be looking at the manometer. So a manometer is simply an instrument for measuring gas pressure. The manometer is simply an instrument for measuring gas pressure, or you can say pressure of a gas. Okay, in the laboratory, or the basic manometer we do use in the laboratory is known as the U-tube manometer. So how can we use a U-tube manometer to calculate the gas pressure of a certain gas? So note that the U-tube manometer has two openings. It has two openings, of which one of the openings is connected to the gas supply. One of the openings is connected to the gas supply, and the other opening is open to the atmosphere. Is open to the atmosphere, of which the U-tube manometer is either filled with water or mercury. So this is filled with mercury because it's having a concave meniscus. That is the concave meniscus on the surface of the water. This is a concave. Sorry, it's a convex meniscus and not concave. It's a convex meniscus. Then when it's filled with water, it will have a concave meniscus. So this is a concave. A concave, that is a downward bend. A concave meniscus. Okay. So we have three cases or three conditions that will be applied in order to be able to measure the pressure of a gas. The first case is when the pressure of the gas supply is greater than the atmospheric pressure. Greater than the atmospheric pressure. If this is the case, we are going to have the diagram to be looking like this. So this, the limb on the left side is connected to the gas supply, of which we are going to measure the pressure. Then this other limb is open to the atmosphere. So atmospheric pressure is entering. So we denote our atmospheric pressure. We denote our atmospheric pressure to be equal to uppercase H. Then the gas pressure will pass through this limb. We denote it by P. So the gas pressure is equal to P, and we have the pressure difference that is in height. The pressure difference to be lowercase h. So when this is filled with mercury, remember in this case the pressure of the gas is higher. So if it's higher, meaning the limb, the mercury on the atmospheric limb will be higher than this, because when the pressure of this gas exerts on the liquid, that is the mercury here, the mercury will rise on this other limb. You get? So in this case, we are going to have the pressure difference, and this pressure difference we call small h. So if this is done, the formula to calculate the gas supply pressure is given by P equal to uppercase H plus small h. That is for case number 1, where H stands for the atmospheric pressure and small h stands for the pressure difference. So we are using this formula in terms of centimeter of mercury, millimeter of mercury, or meters of mercury. Or it can be P equal to P of H, P of uppercase H plus P of lowercase h, where P of uppercase H stands for the atmospheric pressure, in this case in terms of its standard SI unit, and that is Newton per meter squared or Pascal. And P of H is equal to the pressure difference, and this pressure difference is equal to the density of the liquid, which is mercury we are using, times the height, that is this height here, that is this height, times acceleration due to gravity. So for us to get the value of this pressure difference, we are using this formula. And remember, it's in terms of Newton per meter squared or Pascal. So we are using this formula when we are dealing on Newton per meter squared or Pascal, but we'll be using this when we are dealing on centimeter mercury, millimeter mercury, or meters mercury. So for case number 2, case 2, when the gas pressure is equal to the atmospheric pressure. So in this case, if the gas pressure is equal to the atmospheric pressure, we are going to be having the diagram of this, so that when the gas pressure exerts, or gas supply exerts, a certain pressure on this limb called P and is equal to the atmospheric. So if it's equal to the atmospheric, you'll notice that it won't change, showing that the pressure of the gas here is just equal to the atmospheric pressure. Remember, in terms of centimeter, millimeter, or meters of mercury. Or P is equal to what? P of H in terms of Newton per meter squared or Pascal. And for the last case, when the gas pressure is less than the atmospheric pressure, the diagram will look like this. So since the gas pressure will be less, you notice that the atmospheric pressure will exert more pressure than the pressure coming out from the gas supply, so that the height of mercury on the gas supply limb will be higher than that of the atmospheric. You get? So in this case, we are having the pressure difference to be here. And what will be the pressure of the gas? The pressure of the gas will simply be H minus H. Remember, in terms of what? Centimeter, millimeter, or meters of mercury. Or it is equal to P of H plus, P of H minus P of small h in terms of Newton per meter squared or Pascal. Now take note, we have some basic units in pressure. So we have the Newton per meter squared, we have the Pascal, we have bar, and we have the millibar. So 1 Newton per meter squared is equal to 1 Pascal, and 1 bar, short form is B, that is 1 bar is equivalent to 10 raised to power 5 Newton per meter squared, and 1 millibar is equivalent to 10 raised to power 2 Newton per meter squared. Also, it can be 10 raised to power 2 Pascal, because 1 Newton per meter squared is equivalent to 1 Pascal, right? So these are the basic units of pressure.